Hi, Robert. Thanks for joining us. I think you mute yourself.
There you go. Can you hear me now?
Yeah,
Very good.
cool. Very good.
Perfect. I don't know if you can see my screen, but I think, or see my video, correct?
Yeah, we can see you.
Okay, perfect. I'm Aaron introduced me to this, so I'm glad to be able to join and participate a bit and talk about what we're doing. I don't know that my presentations will be as technical as yours, but we're certainly making use of BOPTest, so I'm glad to be able to talk about it.
Awesome. All right, so I think we'll get started. Welcome, everyone. I'm Zoltan. I'm on the IBIPSA Education Committee, and I'll be hosting the webinar today. We have two cool presentations by Gao and Robert about BOPTest in action. We'll start with Gao, and then we move to Robert, and then we'll take Q&A after. Before we go to that, let me just remind you a little bit about, about the education committee's purpose. So the point of our committee is to find education training needs for our community, especially for building simulation in academia and the private sector. We also try to find new educational material and methods that benefits our community. And then every now and then we offer training sessions for both members and non-members. And then, of course, the whole point is to promote the best use of and best practices for building simulation in buildings. Everything we have done so far, you can find on the BIPSA University YouTube channel, including the talks today. If you have to jump off earlier, if you want to rewatch it, shortly after, you will be able to find these uploaded. And then already a shout out to next time in about 2 months, in March 26th, the next BOPTest webinar with Flavia and Lucas, who will talk about their work, including how BOPTest moved to DOPTest, the district optimization and testing framework, and extending that to multiple buildings, which is pretty cool. And then obligatory, if you want to support the BIPSA, please subscribe to the journal. Actually, and you get access to the journal. You will get a supporting member logo that you can use, and it's not really that expensive. And it will help us to continue offering this kind of awesome services and serve our community. Okay, with that, I'll invite Yuan to open your mic, your video, and share your screen. And while you do that, I will introduce Yuan. So our first speaker is Yuan Gao. He's currently an assistant professor at the International Institute for Carbon Neutral Energy Research at Kyushu University in Japan. He earned his PhD from University of Tokyo, also in Japan. His main research areas include time series forecasting with deep learning, reinforcement learning, renewable energy control, interpretable deep learning, model optimization, and application of large language models. He has published 15 academic papers as the first author in journals such as Applied Energy. And before you kick off, Yuan, let me remind you that, or remind our audience that you have a Q&A button at the bottom. And so as the presentations go, please punch your questions in there. We will collect everything and do the Q&A session after both presentations. And so with that, Yuan, floor is yours.
Okay, thank you so much. Thank you for the introduction, and hello everyone. And I'm very glad to give you the presentation about my previous experience about how to use BOPTest. And it's basically about the model predictive control and the reinforcement learning, as those two algorithms are listed in the website of BOPTest, and this is the original meaning why we developed the BOPTest framework. And I will go with two examples, and one is about model predictive control, and the second one is about deep reinforcement learning. So let's go first about the model predictive control. It's I'm just introducing the paper right here. It's just published in 2023. It's about the we call it the tube-based robust model predictive control. So it's relatively different with our traditional concept about model predictive control. So I will show you how to go through this way and what is the usage of BOPTest here. So before we start the contents of this paper, and I would like to give you a brief introduction about model predictive control. And I believe that all of you are very familiar with this algorithm, but I need to mention here a very simple but easy to ignore, a very simple factor, but it is very easy to ignore. It's about the uncertainties. So basically, the MPC is just about we have a prediction horizon. It's, for example, like the future 24 steps, and we have the control horizon. Usually, it's just the future 1 step. And we finish the prediction and doing the calculation, and we got the control signal for future 1 step. And we apply this control step into our model systems, and we just move this prediction window and the control horizon 1 step forward so that we can just finish all the MPC. But in this case, when we just doing the manipulate inputs and we get the observed output here, which you can see is the dashed line in green in this figure. And we have another target trajectory, which means that this is our ideal optimization target. And the dashed line in green is just the output we really got, we really observed in our optimization. So it's not totally same between each other because we have the uncertainties. The first uncertainties is about the forecasting, because we are doing the operational optimization for HVAC for the indoor air temperature, and we may do the forecasting for outdoor air temperature, solar irradiation, etc., numerous meteorological hyperparameters. So we cannot do 100% accurate forecasting, of course. So this is the first uncertainties. First uncertainty comes from, and the second one is about the RC model, especially in the BOPTest when we are doing the MPC work here. We need to first use a RC model to replace the Modelica BOPTest model and just combine the RC model within the constraints, within the cost function of MPC and doing the calculation. And finally, we just test the control signal into the Modelica BOPTest. So there is 2 uncertainties. One is from the forecasting and the 2 is from the RC model. So basically, this paper is about dealing with the uncertainty about forecasting here. So it is about the forecasting in MPC. So conventionally, we have like 2 kinds of MPC. The first one, we call it a robust MPC, RMPC, and also the statistic MPC. So those 2 algorithms are really common in the previous research. For RMPC, it's about we need to consider the worst scenarios, and the SMPC it's just dealing with the approximating and resolving the uncertainties. But in my previous research, it's about the method I call it the tube-based MPC, and this is what where this algorithm comes from originally. It's a paper in 2005. From my literature review, and this is the first paper mentioned tube-based MPC, and it's basically a mathematical proof for the tube-based MPC about its convergence, about its effectiveness in the linear system. But when we consider about the BOPTest, about the HVAC, the Modelica models, they are all nonlinear systems. So in this research, there's no serious mathematical proof of this algorithm. We just first apply this algorithm into the BOPTest and to verify if it will work in this nonlinear system. So this is what the two-based MPC looks like. It's about two kinds of MPC. First, we call it nominal MPC, and the second one we call it the ancillary MPC. So the nominal MPC is just the open loop MPC to calculate the target trajectory, as I just mentioned previously in the first figure of MPC. And the ancillary MPC is considering about the uncertainties. It's just like a tube because the forecasting results could be generated anywhere, inside this tube. So it's basically deal with the prediction uncertainties, and we just need to narrow the distance between nominal trajectory calculated by nominal MPC and actual trajectory calculated by the ancillary MPC. So as long as we just narrow the distance, we will have a robust MPC to deal with the forecasting uncertainties. So this is a proof from the linear system of two-based MPC, and I just believed it that this assumption could be just converted into the non-linear system. And we use the two-based MPC as our case study. And in this research, we just do a little bit modification for the tube. This is because when we are doing the forecasting, it is not the forecasting uncertainties are not a straight line. Because when we are doing the forecasting for the future 1 hour, I believe the accuracy will be higher than we're doing the forecasting for about 6 hours later. So we just modify the tube and we just assume that when the optimization window, the time step is close to the current step, so the forecasting uncertainty will be a little bit we will have a small forecasting uncertain space, and when the time step just goes straight forward, and we will have a relatively large uncertain space. So this is our assumption in this research. And this is a workflow of the two-based MPC. So basically, we have the open loop nominal MPC to calculate the trajectory. And after that, we have the ancillary MPC to calculate the actual trajectory. So, and in this situation, when we are doing the ancillary MPC to calculate the actual trajectory, we need to narrow the action space in MPC. This is also the idea from the original paper of two-based MPC. So, for example, in BOPTest control, we may have the control range for the inlet air temperature is from 50 to 35, for example. But in the ancillary MPC, we need to narrow our action space. Maybe from 50 to 35 becomes 18 to 32. So we just narrow our action space. And this will just ensure the convergence of ancillary MPC and the two-based MPC, the whole framework. And so this is what we call the ancillary MPC and the nominal MPC here. And here is a case study, and you can find the detailed information in the website of BOPTest. It's about the best year, and we have two kinds of control action. The first is about supply air temperature set point, and the second is about the control signal for the air mass flow. And of course, first we need to build the RC model, and here is about 2R2C, and it's for a very short period, among the data set, and we calculate the mean absolute percentage error is about 50 percentage points here. It looks good, but As I just said, this is the first uncertainty comes from the RC model. And this is our objective function. Basically, it's about the operational cost and the indoor air temperature control. And so it's a balance between two operational optimization targets. And since we need to deal with the forecasting uncertainties, so we have the real measured temperature inside the BOPTest, and we could just add the random noise for the forecasting uncertainties, and to see if the two-base MPC could deal with those forecasting uncertainty space very well. So of course, we need to compare with the conventional MPC models, including the open loop and closed loop MPC. And here's a very important thing is because two-base MPC, we do not have any further information comparing with the closed loop. So if we compare with closed loop and two-base MPC, it is basically we could find out if the two-base mechanism will work in this case study. So here is the final results here. And so you can see M.3 is two-base MPC and M.1 is open loop. M.2 is closed loop. So we have constraints 1, 2, 3, 4. It's just about the tighten for the action space. So originally it's from 0 to 1, but in constraint 1, we just narrow it to 0.1 to 0.9, and constraint 2 and so on. Of course, for the temperature control range, we just narrow it to from 13 to 39 to 20 to 32. And here is about the operational cost and the average distance to target trajectory, because we have a very strict indoor air temperature setting point in this case study. So it's about 50 percentage points for the operational cost saving and relatively good performance in the target trajectory. Final case study here, and as you can see, it's although the matrix indicators they look good, but in the real visualization results still have very large uncertainties. Still is about the RC model and the forecasting uncertainties. We needed to deal with all those uncertainties so that we could get relatively good result in MPC. And of course, that's all for the MPC part. And here I would like to move to the deep reinforcement learning part. As you can see from the title, it's about the predictive information. Why I need to mention this is because in the traditional deep reinforcement learning algorithm, we usually do not include any future information in the state vector. Of course, we need to include the history vectors so that to make it a Markov decision process. But usually we do not consider the prediction. But here comes to my mind, what if we just include the predictive information into the deep reinforcement learning, and how we could deal with this part to get a better performance comparing with the conventional deep reinforcement learning. So here is what the idea looks like. So in the state vectors, we have, from my perspective, two kinds of state vectors. The first one is the non-time series, such as the state of charge of batteries. It's not included in BOPTest, but we still have those kinds of things. And the second part is about the time series part. It's like the indoor air temperature, solar irradiation, in the future forecasting, etc. So basically, in this idea for the actor network and the created network, we share the same feature extractor networks here. So basically, we just divided it into the two kinds of vectors. For the non-time series data, we just deal with the MLP. And for the time series data, we can deal it with the transformer encoder, with the recurrent neural network, etc. And we could find out if this method will work here. So still, we use the best air BOPTest case study in this research, but we just tested multiple scenarios: pin heat, typical heat, pin cool, typical cool, as it's just showing in the website. It's the recommended testing scenarios. And oh, sorry, here is a result. And MDO1, we do not include any predictive information in state vector. And MDO2, we just use simple MLP to process the time series state vector. And MDO3, we just use a GRU. It's a kinds of long short-term memory and the recurrent neural network to process the time series data in the state vector. So as you can see here, we can just get a relatively small operational cost saving, but very large in the indoor thermal comfort index. And this index was calculated by the BOPTest itself. So this is, I think, a very good advantage of BOPTest in reinforcement learning, because we do not need to consider the design of reward function, which is very important during the training of the algorithm. And give you the visualization of typical heat here. And I think we should remember that MDO2 and MDO3 is just we have the predictive information. And as you can see here, it's we call it preheating, so that we could save some operational cost. And the similar result in the typical cool. And yeah, here we just since it is very close to the running schedule that no one is in this room, so the algorithm just slightly just stop the HVAC system and to save the operational cost. And you can see everywhere for the preheating and pre-cooling. That is what the predictive information brings to the reinforcement learning. Okay, and I just gave a brief introduction for the how I use BOPTest in MPC and reinforcement learning. So here I give I gave a relatively 3 points of summary here, and I think BOPTest provides a stable framework for testing MPC and deep reinforcement learning. And no matter how complex the algorithms are, you could just have a stable testing platform without any further detailed explanation. And you have the stable reward function, stable operational cost casting, operational cost calculation, and this is very important. So you could focus on the algorithm itself. And of course, we can just compare different algorithms, MPC and reinforcement learning simultaneously through the same framework, same data. And also, you may find the introduction, and they are just bring the BOPTest to DOPTest, which may have multiple buildings. And this is also my future work, whether the multi-agent reinforcement learning could be used and tested in the complex BOPTest. We call it DOPTest. And this is my future consideration for using this framework. Okay, that's all for my presentation. Thank you so much.
Very good. Thank you. Thank you, Yuan. So if
Thank
there are
you.
questions, please put them in the Q&A box, and then we'll come back to them after the next presentation.
Okay.
Sounds good. Thank you. All right. So our next presenter will be Robert. And I think assisted with Aaron, if I understand this correctly.
That's
Okay,
correct.
okay.
Yeah.
All right, so why don't you guys start and then we'll see where this goes. Introduce
for sure.
yourselves so I know what
Um,
happens.
I think this is my first opportunity to speak in regards to this. So I'll give you a little bit of background for myself. I'm the Advanced Support Director for Distech Controls. And I get involved in all of the cases, a lot of the training, complex problems and solving, and some of the commissioning and the direction at which we kind of push customers and train customers on our products. And so I had a few issues. I had a few problems I was looking to solve. We have difficulties around training customers on our products and tuning PID loops and these types of applications. But we also have some issues with supporting customers and not just on the product itself, but on how they were sequencing, how they interpret sequences and apply them to the controllers. And I discussed a lot of these issues with Aaron over the years, and he introduced me to BOPTest. And I was very, very interested in the practical applications of BOPTest in what we do today for training, for support, and for demo. I know Aaron kind of pushed the envelope in some other areas, but I was particularly interested in the support element of it because the ability for us to have a simulation and run applications against it allows for us to validate programs and validate work that the customer is doing and compare it to code and sequences that we provide them to see the different outcomes and to help encourage them and train them in better practices. So some of the things we've done with this and we will be doing is we're going to use BOPTest as part of our simulation in our AHR booth that's coming up, I believe, on the 10th. So we'll be doing AHR and we're going to have 3 BOP simulators running. And I think I can share my screen briefly and introduce that. Let me see if I can share that. I don't think this computer's allowed to share, but Aaron can bring up the screen share and we'll demonstrate that. But I bring Aaron back into this because he's more familiar with the product. And I'm at the current stage, I'm mostly doing the practical application for the demos and the training. So I'd like to have Aaron introduce what he set up for the broker and how we're using it to interface with our virtual controllers and physical controllers so that we can tie BOP Simulator into a real controller sitting in the field tied to actual hardware. Aaron, are you available? Can you talk?
Yeah. Can you guys hear me all right?
Yep.
Yeah, so introduction, my name's Aaron Fish. I recently changed positions. I had moved on from Distech. I was the product owner in the R&D, and I went to work for one of their customers, but I'm really excited about this project. I think it has a huge potential in many ways. And so I'm happy to be here and talk, just more from like a personal side. I just started, so we'll see if I can convince them to get interested in it. But when I was at Distech, it's funny, when you're a controls contractor, you do projects, you get lots of toys to play with, air handlers, chiller plants, and you get to experience them and you get to learn in that environment. Obviously, you can't do whatever you want. You could, with the equipment, you could damage it or you could make somebody uncomfortable. But all in all, you get that real world experience. And when I came to Distech, in a different role, I lost that. I don't have air handlers to manipulate and play with and test things on. And I was looking for something that could fill that void for me, because as a representative of the customer, I need to live in their world as much as I can so that I can understand them. And I ended up, there's like a forum in Discord with a bunch of nerdy controls guys, different people. And there's a gentleman there named Andrew, and he recommended I look at BOPTest and get in touch with David Bloom. And I did, and started looking at it, and found out that it was actually way more than I was looking for. It had a lot more potential. And if I kind of go back and think about what in the BAS world, what does training look like today? What that looks like is you typically go to the manufacturer, you get trained on their product for a week, and then oftentimes you kind of get thrown to the wolves. So you go out on a project, you start up controllers, you look at equipment, and you have to learn via trial by fire. And you often in that environment, there's a lot of pressure and there's time constraints, and there's also
yeah, and just to add to that, we train over 2,000 individuals a year on controllers and our programming and our software packages. And we have over 10,000 cases per year that we're trying to work with customers to solve. So we have to do that with a limited number of individuals. And that's why, to your point, Aaron, this was such an interest to me, because the ability to give people who are training simulations, or the ability to kind of work with hardware that is simulated so that they can actually use the product in the manner they would in the field, is invaluable.
Yes.
And yeah.
Yeah. A lot of it's tribal knowledge too. You go to work for a company, you go out in a project, there might be somebody else with you, and they're trying to give you this tribal knowledge of how systems work and how they work together, and the behavior when this happens. Anyway, and it's a struggle in the industry. Obviously, this industry has a hard time with finding people and getting them up to speed. And then on the other side, the application. So a lot of times, Distech customers they'll write these controller code. They'll write it in the office based on a sequence of operation. They'll simulate the code with no data associated. So they'll try to run it through the paces as best they can. And it doesn't always work. It doesn't always find all the things that they would like to find, because it's difficult. You override things. It doesn't behave like a real system. Oftentimes it just gets to a point where you say, it looks good enough to me. Now, with BOPTest and having a building simulation that behaves like a real building, those two things could dramatically change. Training on people on your system or any system, and you have live data, is way different than like no data or simulated data. It's just conceptually so much better. And then application testing, writing an application and then running it against BOPTest and seeing how your application performs. Does it do what I intended it to do when I put it in through these exercises? And it's really amazing, because it's repeatable. I can run BOPTest, I can put a date and time in, and I can get that same environment again and again and again, which is it's pretty much there's nothing out there like that. So in my career, this is something that I've been waiting for, and I think it has the potential to have ramifications across the board in the industry. But that's kind of the overview. Let me get into the details and show you some things. Let me share my screen here.
And I think Aaron's going to bring up his screen, but what we did together was Aaron built he took the container, the Docker file that was presented, and he also built a broker to translate the commands and messages and the data from BOPTest into our controllers. And so you'll see he has, when we bring it up, you'll see he has two containers running. And we put those inside of an LXC container in Incus so that we could deploy them at scale and quickly. So you'll see that here. Go ahead, Aaron.
Yeah, so I thought it would be helpful it's hard to really conceptualize what's happening. So I thought I would run through this just to help people get their minds around it, because I feel like it's just hard to explain. It's better to see it. Plus I'm a visual guy, so seeing things visual is very helpful. But this is a flow of what's happening in real time, and I'll get to that, but I want to go over this first. And these are the different components in the setup that we have. So the first is obviously the BOP web service. We have that running in a Docker container. And initially, when I looked at BOPTest, I saw that it had a BACnet interface where you could interface with the service through BACnet objects. And that was interesting, but the fact that the Distech controllers have a RESTful API, that was the route that I decided to go, and there's a couple reasons for that. I felt that we could do the exchange a lot faster via REST as opposed to using BACnet. And then on top of that, in the application side, if I were to use BACnet, I would have to modify my applications to bring that data in. And I didn't want to do that. I wanted the applications to be the ones that will get put in the building untouched. And they didn't have to be, no one had to go in and manipulate them to get it to work with BOPTest. And to do that with maybe it's possible, but it just didn't, when I was assessing how I was going to lay this out, it didn't make sense in my mind. So I ended up creating a little project, and it's open source, called the BOP Broker. And basically what it does is it lives in between the Distech physical controllers and the web service. And it does a few different things. At first, it initializes the test case. So it tells the BOP service, initializes, and the test case that we've really focused on is multi-zone office air simple. It sets the step time and the start times, and those are variables that the user can configure. So the user can go in and say, hey, start in January of 2020 or July of 2022, whatever. They can set the time that they want so they can get that environment. And then what it does is it moves the web service forward in time by that step time. It takes the values that the service provides, it writes them to specific endpoints on the controllers, and then it reads specific endpoints from the controllers and writes them back to the service and loops. Oh, just does that over and over and over.
And so, Aaron, what's the throughput on the API for that? Have you noticed?
I've ran it at various times. I've gone below a second. So I've run it at, not for a long period of time, but I think I took it down to 50 milliseconds.
Yeah, we were typically testing in all of these controllers round trip. We were testing 5 seconds without an issue. Yeah. Reading and writing all values via the API. Yeah,
I like the speed because it got me closer to the real world, right? Because those sensors in the controller are going to go really fast. And by writing quickly, it simulates closer to reality. But it's valuable. In training, that might not be the case. You don't need that, so being able to manipulate that time is a nice feature. Now, the user would set up what points they want to write to in the controllers, and there's some JSON files that match the point in BOPTest web service to the BACnet object or input, BACnet input that you want to exchange with. And so that's all set up, and that's, like I said, that's in the repo for the multi-zone office simple air. Let me bring that up. But the key point I want to point out is that Distech controllers are running their own code. So there's an air handler program, there's VAVs, the chiller and heat pump are just read-only in that test case, but the air handler and VAVs are bidirectional. So what's actually happening is the logic in the controllers is controlling the model. And it's mind-blowing to me.
And I'll jump in right there. Aaron, on this note, for this same diagram, we mentioned that we'll be using this model at AHR for our demo. And the controllers you see here, while Aaron is showing them, they are physical. For the demo we'll be doing in AHR, the controllers are actually fully virtual now. So we've actually, the entire setup from BOPTest to the broker to the controllers themselves with the API, it's been entirely virtualized so that we can run it and spin it up and have as many instances as needed for demos and training.
Yeah, and that in of itself, I mean, I could think of a world where in training, you sign up, you get your own little instance of BOPTest and your controllers, you log into a web page, you start manipulating things or doing what, then you turn it off, you throw it away. I mean, today, when you want to do training, you have to have a physical panel and it needs to be shipped to you if it's remote, or you have to travel in, and then there's all this setup time, and then there's taking it all apart and resetting it for the next training. And this is just throw it away and get another instance of all these containers and give it to the person. But so we've done it on physical and virtual. And then on top of that, the controllers are talking to each other via BACnet. So in this case, the VAVs and the air handler are running G36 sequences. So there's all the communication between them, the sharing of data for that sequence is happening in real time, and it's being fed the data from the BOPTest. The VAVs are telling the air handler information, like what's my damper position, what's my room temperature, what's my CO2 load, and then the air handler is telling them, here's my discharge air temperature, you need to do this and that. So that all is happening, and it's like a real project, a real building, and except I can do whatever I want with it. I can blow up the ductwork. Can't do that in a real building, right? You can you can manipulate it in ways that you wouldn't be able to. So hopefully this helps illustrate the whole setup. I'm not going to go through the repo. I'll just show it to you, but it's open. Anybody that has a Distech ECY2 controller could potentially set this up. All the settings are in here, all the config files for the points. I have written a nice overview of how to set it up and structure it. So anyway, that's out there for anybody to use. But let's jump in. So as Robert said, we have this instance that I'm going to show you is virtualized, but just so you can see that we're running the broker as a container. We run the BOP web service, the 0.7 in this container, and then here's all of our devices here. Other than just showing you this, I'm not going to dig in much deeper. I don't know that there's a lot of value in that, but
No, I just showcasing that we took those containers and we put them in LXC instances so we can more easily deploy and control them and group them if needed. And so this is, if you are attempting to run this or play with this, I highly recommend looking at something like Incus, because while they are OCI containers, they are Docker compatible. You can, with LXC, you can group those and do a little bit more, and it's a little bit easier to create your test environments. Here we have them all as individual, but you could just as easily have all of the controllers in the BOP broker and service in one LXC container and run it that way. And so it's a little bit. I recommend it highly if you're working with this at scale. It makes things a little bit easier to iterate and snapshot and control.
Excellent. Yeah. So let's take a look at one of these virtual controllers. So right now that the broker is running, it's exchanging data in the background, the web service is running, and this is the controller here. It's virtualized, obviously, but it could be a piece of hardware that it gets interacted with. And this logic is running, and the inputs that you see here, like this discharge air temp, the flow, these are coming from the model. And this controller the broker is taking the data from it and commanding the model. So for example, if I do this, if I go to my discharge fan speed, it's at 68% and it's maintaining pressure, and I override it. Let's go to 100. We can kind of watch what happens. The pressure shoots up, as you would expect in a real air handler. You speed it up, it's going to build pressure in the ductwork. Now let's take a look at the VAVs, because I have them up here, at least one of them anyway. So here's this is the corridor VAV, and if we watch, if you see, the airflow shot up way beyond set point. So now the damper is closing, which you would expect in a real project in a real building. So this is really, to me, mind-blowing. Like you don't have this unless you're in a real building on a project with people. Having it in a virtualized environment and being able to share it, and then if someday this became ubiquitous with the building industry, I could see a future where, today we have mechanical drawings and architectural drawings. Well, I could see a future where this building model is part of that. And now that gets really interesting, because I could build the entire BAS out, all the code, and interact with that model before the building's even built. So it could change building commissioning. It could change the whole process of how these systems are implemented. Because the time saving too, like you had a virtual Sorry, go ahead.
No, I was gonna say, and for us for the training and support element of it, we're interested in it primarily because we can write code and run it against the model, and then when we see differences in the real building or in the application itself, we can compare those to determine if we have issues with hardware, if we have issues with implementation, software, and networking. These things really help us determine the nature of the problem we see. And I had one question for you, Aaron, on this. If you remove you have the virtual VAVs created to match the ones that exist in the BOPTest. If you didn't run one of those virtual VAVs, or you didn't run that mechanical piece of equipment, how does this interact, and how does that work?
Yeah, that's a good point. In this setup, we have all the equipment, the air handler, the VAVs. If, for example, I just wanted to focus on the air handler, I didn't care about the VAVs, I could run this, run it in a way that I only interact with the air handler. And because you folks already built control algorithms in the model, the VAVs will just be controlled by the model and happy do their thing. I don't have to pay it. So I can take pieces of the model and interact with it and leave the rest alone if I want. So it's flexible in that way.
Yeah, this is the training element for us. This is the element for what you did here, Aaron. This is why we're so interested in training, is because we can take just the VAV out and train a customer just on that piece, and we don't need to interact with the rest of it. We can run them through it. We can show them how to tune a PID. We can show them how to write code or implement our code, and they can see what happens when they make mistakes without doing it for the first time on a job. They can do it in training and actually see what happens if they don't correctly tune the PID loop or correctly set up the parameters on the VAV, as an example. So a very simple thing, but it's actually very difficult to train somebody on how to work with a VAV without having one there. It's a hard thing to do. They usually end up having to learn on the job, and that causes a lot of man hours to be wasted and a lot of unnecessary tickets or tech support calls for our teams to handle that. So we're very interested in the training element of this.
Yeah, one last thing.
Robert, Aaron, let me give you a 1 minute warning.
Yeah,
okay, 1 minute, and then we can move to Q&A.
Yeah, we could take up a lot of time talking about this. One last thing I wanted to show in particular was, this is the discharge air temperature off of the air handler in this test case, and you can see it's oscillating between 55 and 70 degrees. So that PID in that controller is not tuned. So what I wanted to do is just kind of demonstrate this live. This is how's that look? It's probably really small.
No, it looks fine. You can see it.
This is a graph of the PID loop. So the orange line is the set point, and the green line is the sensor reading, and then the blue is the output. And you can see the output is oscillating from about 45% to 74%. So that chilled water valve that's in operation is just going open, closed, open, closed. And I can tune this loop. I can teach somebody how to tune a loop using this, which you couldn't do that before. You taught them the algorithm, what the proportional band does, what the integral band does, and so on. You gave them the concept, and then you throw them to the wolves, and then they have to figure it out. Well, in this environment, that's not the case anymore. I can teach somebody right here how to tune a loop, and they can play with the numbers and see how things react. And it's, if there's any controls guys in the audience, you're probably nodding your head saying, yeah, I know what you're talking about. PIDs it's a mysterious thing
to train on
this world to help people understand. But with BOPTest, that's not the case anymore.
Yeah, I think we're at time, Aaron.
Yep, perfect.
Very good. Thank you so much, Aaron and Robert. I could listen to this all day, but we have to come to an end.
We understand.
Yeah, I know. So we do have questions in the Q&A, and again, a reminder, if you have some more, plug them in there. I'll read them to you, and they are mostly for you guys. So let's see. Ed Morris is asking, what effort was involved in virtualizing your controllers?
That was I was involved quite heavily in that, and that was an intentional effort, because we looked at the the platform we used to run it, and there was a development tool that we could run on our laptops. And so really, from a developer standpoint, the pieces were all there. We just decided to run them initially in a containerized environment, kind of as a proof of concept. And then we used that to make, with BOPTest actually, to make the business case with our organization and to the R&D team that we needed to make an official version of that virtual controller. And so I'm happy to say we will, while that's not a product yet for Distech, that virtual controller, it is something that we have official support with R&D, and now it's part of our pipeline. And so with every product or every firmware revision, we now have a registry that we build out that container, and we can use it for testing. So I can run a simple command, spin up BOPTest, and run a test against that container that was just built, and run the same test I did last time and compare the results and validate that they still work the same way. Or if there's some difference, I can jump in there and quickly address it. So it's already starting to bear fruit, but we're in the early stages of figuring out how to combine these test cases and maybe automate some of these steps. So I would say there wasn't a lot of work for me because the developers had done a lot of the heavy lift, although the initial demos and container I built. But and for me, the virtual containers are the real key to this process, because with us having BOPTest running in a container and being able to spin up the virtual controllers that have code already running in them to interact with that gives you a really quick and fast way to use that simulation to prove out that you don't have any issues in your code base or in your product, or just to validate the test sequence goes through and completes without error. So.
Thank you. Yeah. And then follow this up. Like, could you do something like this and apply them directly to the real hardware, as like hardware in the loop testing on control?
We already do that. In fact, I'm glad you asked. For AHR, we virtualized about 30 controllers, but we also have an additional 8 that are real. And so they are intermixed within the virtual. The 8 physical controllers are intermixed in that, and they interact. We're using Back.sc and a cloud-based SC hub, and so all of the communication goes to the SC hub, and the controllers all communicate on that hub, and then the bot broker talks to each and every one of the controllers with API calls, with RESTful API calls. So
yeah, Ed, that the broker that's in GitHub now, the bot broker that's in my GitHub now, is the second version, and the first version was more of a proof of concept. And what I wanted to do, so one of Distech's controllers, it has an ARM64 CPU, and it supports containerization on the hardware. And I would have loved to get all of it into one device. And we even had this concept of building in a box, because it's the controller, the web service, the broker, all in one. And David Bloom will probably laugh, but something about the Modelica, there's a Python package in Modelica that's not supported on ARM64, and I beat my head trying to recompile it, and I gave up. But we have another device that's AMD. I was running the web service on AMD, and then I had the broker in the Distech controller container, and then the code. So I think your question was, I think what you're asking, correct me if I'm wrong, but what we showed was all virtual, but it really doesn't make a difference. You can run the service, the broker against a Distech device that has the REST API. It can be hardware or the virtual. And then initially we used the hardware.
Okay. Yeah. And Parisa was asking, is there a way to look at it? Can you put a link that people can check out to your GitHub or anything that's public?
Yeah, I can put the broker GitHub in. The thing that I just want to emphasize, though, is that to do the setup, you would need a Distech piece of hardware, the device. So that broker, the broker that I made, is really only valuable to people that have a piece of hardware. The virtual version is really internal use only, right, Robert?
Okay. That's clarified.
There is a provision for if we're running the virtual environment in our demo, and you would like access for a period of time to a demo login. I can't distribute any virtual controllers around, but I can host and give access to, if someone would like the opportunity quote unquote demo the product. That we can accommodate. So I don't know if my email was in the PowerPoint now, but you can feel free to list my email there. And if somebody would like to demo the product, we can give them a virtual controller to demo. And that controller, you would be able to make API calls to it and use that broker with it, or multiples if you need to. So you'd be able to load code and do that, but that would be strictly kind of in a demo mode. So you'd be able to use it and play with it, but we couldn't give it to you yet because it is not currently, the virtual controller is not currently considered a product. But the good news is if you did do something in the demo environment and you liked it and you did get a physical controller, it would work the exact same. So you would have the same experience. So
nice. I want to circle back to Yuan's presentation. There's one question for him as well from Bertrand, and he's asking for the MPC uncertainty question. Did you test other types of uncertainties as opposed to only the random noise and random walk or some kind of drift, and how did that perform?
Yes, thank you so much for your question. Yeah, actually in that paper, I did not test the random walk, and you may see from the figure that, I'm sorry. You may see from this figure that sometimes the uncertainty scenarios are not really a time series data. Yeah, to be honest, the really time series data cannot like this. Yeah, so, but I saw, because in this case, my perspective is that we may use the generative deep learning models like GAN or like diffusion model to just generate the time series, uncertainty time series, which is very close to the real situation. But I did not test it in this manuscript, but I saw the other research is about the linear system with the random walk uncertain space, and tested with the tube-based MPC. And I remember the author is from Oxford, and the results shows that tube MPC also worked if you use the data drift noise or random walk, very smooth forecasting uncertainties. And yeah, and I think I will test it later, and I believe this will also work because it did not change any assumption for the tube-based MPC in nonlinear program. Thank you.
Yeah, thanks. And if I have one question for the same project, and maybe for a short answer, because you mentioned you saw very good metrics, like when you showed your tube MPC results, but then you showed the time series and you said there's still some discrepancies. And so I wonder if you have a feeling for better metrics that we could use, so that the good metrics on the controller performance are not masking the suboptimal performance here, or this.
Yes, absolutely.
Swing.
Yeah. I believe it's because the trajectory, the average temperature trajectory, the calculation is not good to demonstrate the curve here, and it's mainly considering the operational cost actually. So yeah.
Yeah, so you have a feeling for a better metric that would capture better what you want to see?
Yeah, basically, I think currently my idea is just the balance between the numerical calculation. For example, in the reward design in reinforcement learning, it's almost the same question because you have two operational targets, and one is operational cost and one is the indoor thermal comfort. And actually, it's very hard to keep the balance. So usually it's about the numerical. So basically one is around -1 to 1, and the other must be the same scale between -1 to 1. And after you set the scale, you could slightly modify the weights between those two reward functions, and Yeah, I think if you do this slightly with the setting with the design of objective function in MPC and reward function in deep reinforcement learning, you will make this curve looks much better than the current situation. Yeah.
Perfect. Thank you so much. We're at the top of the hour, so thank you all the panelists for the nice presentations. A reminder for our listeners to support the BIPSA. You see the breadth of our simulations from academic to super applied. It's awesome. And with that, a reminder for the next BOPTest webinar on March 26th. Sign up, come and listen, and enjoy the show. Thank you very much.